Hello students, today we are going to discuss about the Cauchy-Riemann equation for Cartesian coordinate and the application of Cauchy-Riemann equation. Actually, the Cauchy-Riemann equation is del u over del x is equal to del v over del y, and del u over del y is equal to minus of del v over del x. In this Cauchy-Riemann equation, if u represent the velocity potential of an incompressible steady fluid flow in a plane, and v is the streamline function, that means u and v are twice continuously differentiable function, then the function satisfies the CR equation. That means to prove whether the function of fluid is incompressible or compressible, we require a CR equation. We will take u as a velocity potential, meaning that we imagine a flow of a fluid in a plane such that the velocity vector of the fluid at each point of the plane is equal to the gradient of u. This is the gradient of u multiplied by del. This is the vector operator del, which you have studied in a previous semester in a vector fifth unit of the first semester. By differentiating the Cauchy-Riemann equation, second time we will have u in form of Laplace equation, that is del square u by del x square plus del square u by del y square is equal to 0. And if u satisfies the Laplace equation, that means u is a harmonic function. It is also proved that if the function is harmonic, then it must satisfy the CR equation. This is your next topic, which we are going to study in a next lecture. Okay, this means the gradient is 0, so the fluid is incompressible. For the properties of fluid, CR equation is widely used. Now, for the necessary condition of the function to be analytic is if the function is fz is equal to u plus iota v, and then it must satisfy these two equations, which is the CR equation, del u by del x is equal to del v by del y, and del u by del y is equal to minus del v by del x. To prove this equation, we required that del u by del x, del u by del y, del v by del x as well as del v by del y exist. That means these are the first derivative which is continuous. So proving this, first we required that an increment in x is delta x, increment in delta x. Similarly, for increment in y, we are having a delta y as an increment. Because x and y are involved in a function u and v, so there is an increment in u is delta u, and increment in v is delta v. Increment with respect to u and v, finally we are having increment in fz, so we can say that fz plus increment of delta z is equal to u plus delta u plus iota v plus delta v, v plus delta v, increment because of x and y. Okay, so proving this, first we will consider this increment in x, increment in y. Corresponding to the increment in x and y, we are having an increment in u and v. Corresponding to the increment in u and v, we are having an increment in function fz. For the derivative of function fz, what we required, limit delta z tends to 0, function fz plus delta z minus fz over delta z. That means fz is equal to u plus delta u plus iota v plus delta v minus function u, that is u plus iota v is minus over delta z. So u is cancelled. Similarly, iota v is cancelled. What we have? We have delta u plus delta v, iota delta v over delta z. So we have f dash z, which is the derivative of function z, is equal to limit delta z tends to 0 for delta u plus iota delta v over delta z. This is equation A. This is the derivative of function B. Because z is a function, because z is the function which is equal to, z is the number which is equal to x plus iota y. So delta z is depending upon delta x and delta y. So for considering delta z increment, we required from the previous page what we have, f dash z is equal to limit delta z tends to 0 for del u plus iota del v over del z. Now if we consider for x axis, for x axis y is equal to 0. If we consider only for the x-axis, then y is equal to 0. That means z is equal to x plus iota y is converted into z is equal to x. So the increment in delta z should be equal to the increment in delta x. So replacing this value in equation A, this is our equation A. What we have, f dash z is equal to limit delta z is replaced by delta x, so delta x tends to 0 delta u over delta x plus iota delta v over delta x, which is going to equal to, which is equal to f dash z. By solving this limit, what we have, del u over del x plus iota del v over del x. This is equation B. Now again we are considering for y-axis. For y-axis, what we have, for y-axis we have to consider x is equal to 0. So z is equal to x plus iota y is converted into z is equal to iota y. So the delta z is equal to iota delta y. Now replacing z delta z with iota delta y in equation A. In equation A we have f dash z is equal to limit delta y tends to 0 into delta u over iota delta y plus iota delta v over iota delta y. Iota is cancelled. For rationalizing this term, because iota in a denominator, we are going to multiply iota from denominator as well as numerator. We have limit delta y tends to 0 is equal to minus iota delta u over delta y plus delta v over delta y. To solving this limit, we have f dash z is equal to minus iota del u over del y plus del v over del y. this is equation C. Because equation B and C is both derivative of fz, so comparing both sides for the function fz by equation B and C, comparing both sides, we are having del u over del x plus iota del v over del x is equal to minus iota del u over del y plus del v over del y. So comparing the real part with real part and the imaginary part with imaginary part. So the real part is equal to del u by del x is equal to del v by del y, and for the imaginary part what we have, del v over del x is equal to minus del u over del y. In CR equation definition, we are considering this negative sign on the left side, but it is true either we are considering it on the right side or left side. So the CR equation is satisfied for the Cartesian coordinate.